Thank you so much for your attention. Now we are going to carry on to the chemical engineering panel. We will have Mr. Anwar Mamadli and Mr. Sanan, as well as Dr. Kanan, to join us for the panel. They are just putting on their mics. They will join us shortly. While we wait for them, please do not forget to stay until the end of the session so that we can do our gifting, as well as let you know more about the internship opportunity that might be available for some of us in this room today, as well as the chance to participate in the 3rd Global Engineering Symposium in South Africa. So please just stay tuned for that until the end of the symposium. Thank you for joining us. So Dr. Kanan will be
okay. So that seems working okay? Yeah, okay. So good afternoon. Thank you very much for, thank you very much for having me in the symposium. This is my first participation. But just to briefly introduce myself, I'm a senior production chemist working for BP in the Caspian region. So today I'm going to talk about reservoir souring, its impact and control in the oil and gas industry. So going straight into that. Okay, so basically what's reservoir souring? That's the predicted or observed sulfide production. So this is all really about H2S production in the oil and gas industry and what impact it has to the production. Because I am working in the what we call upstream section in the industry where we produce, rise and refine oil and gas. So this is where we focus on. So the problem with H2S is integrity, first of all, because it damages the metallurgy and it causes potential damage to the structure of the metals. And the other most important one is the safety. H2S, as you will all know, is a toxic gas, and we want to minimize its production during the process. And what are the souring? So what's the causes of it? So the causes in the basically focused around the processes happening in the reservoir. So that can be the natural ones, the temperature, high temperature and pressures, pressure depletions while you produce oil and gas. And the other thing is microbiological. So basically bacteria that live in the reservoir cause the H2S production. Okay. And this is what we're going to potentially focus in here, microbiological souring, why it's happening, and what it leads to. So microbiological means it's all about bacteria. Probably not a very strict analog, but in the health area, we talk about the viruses, coronavirus, all this stuff that cause the health issue. This is potentially analog to the oil and gas industry. We have our viruses in there as well. We don't call them virus, we call them bacteria, but this is the bad actors that can cause damage to the health of oil and gas production. And we classify them, yeah? So the really focused, the main focus we put here is onto sulfate reducing bacteria, those that produce sulfide H2S as a result of their metabolism. And this is what basically happens. So they need energy, like all living creatures, they need energy and nutrients. So nutrients is really carbon from our hydrocarbon, from oil. And the other thing is sulfate that they use to metabolize during the process, and then they extract H2S and other potential gases that can cause the problem. But again, we focus on hydrogen sulfide in this section. Okay, so, and what controls it? So anything that helps bacteria to survive. Yeah, so, and that can be temperature, that nutrients, pH, pressure, and also composition. So nutrients comes from composition, and that can be from formation water or from oil itself, and all the way through other determining parameters that dictate what type of bacteria will proliferate or grows, predominate. And this is basically what happens. You would probably know to extract oil, we would use secondary mechanisms like water injection. So basically, we inject water into the reservoir to extract more oil. And that's potentially one of the sources that we may face in the during the production phase, where over a time the reservoir will go sour, meaning that H2S levels will increase. Okay, so basically what happens is in the area of water injection zone, you have low temperatures by high sulfate and what we call volatile fatty acid levels. This is all nutrients for bacteria. And then we have at the production wells, high temperature environment. So eventually we create a mixing zone where all these different types of bacteria would create consortium. And basically over the production cycle start causing a problem by producing H2S. So if we move on, so that's what we call in situ in the reservoir. But if we go over the cycle, that mixing zone will shift to the production well or production area, and eventually H2S concentration will increase. That will cause damage to the metallurgy while we produce on platforms. And what systems are exposed? This is more a little bit of technical for those who in the petroleum engineering space, or especially in the managing the processing of oil and gas. So production tubings, wellhead, flow lines, this is all different parts of the systems that are at risk if our reservoir goes sour. Okay. And the other thing to know about, H2S will behave differently between three phases. So when we produce oil and gas, it's not just oil, it's three phases. It's gas, oil, and water all mixed together. So depending on pH, your H2S can partition to different phases. At low pH level, that will be mostly hydrocarbons, and then that can go into the species, into the water phase. And different sulfide species will behave differently. And of course, that will dictate the extent of the risks that you have. Because eventually, why you need to understand partitioning? Because what does it have the impact to the metallurgy? This is what it's called NACE standard. NACE is an organization that manage all the corrosion in the industry in terms of the guidelines. So they provided this guideline saying that at certain partial pressures, corrosion can be of a significant issue. Okay, and that's why the other thing what we do, and we talked about here a lot about digitalization, we need to understand what's the partitioning behavior that we might face. That's why we predict these things and model. Which is why we looked into the partitioning behavior and model it, try to calculate it, depending on the reservoir conditions and composition. So this is the principle. I won't go too much into details, but the main thing here, understand your composition of your fluids in the reservoir, understand your temperatures and pressures, and then you use equation of state modeling formulas to calculate your H2S partitioning. So what do we do next? We need to control it. So we said about bacteria, this is the species that cause the problem. So to kill them, we use what we call biocides or biocidal chemical. That's that's the different biocides that are used and their mechanism how they kill basically bacteria. Bacteria are single cells organisms. So different chemistries would attack either cytoplasm or the proteins or basically the whole structure of the cell to destroy them. And this is different type of chemistries. The common one used in the oil and gas industry is hypochlorite, or this chemical is a little bit corrosive, so you need to use alternative ways like glutaraldehyde and THPS, or tetroxyhydromethyl phosphate chemical. And that's one of the things, for the young students and engineers. This is the industry, but we need to think out of the box. So we touch base a lot on that. So what can we do to improve it? What can students or young generation can do to develop new chemistries that can be more environmentally friendly, that would have less impact to the environment and pollution? So basically, that's one of the things that probably next generation should be thinking about. And also, how do we move these controls in a way that we reduce the low carbon agenda? So we reduce carbon footprint. Okay. And the other thing is we need to monitor this. So one of the things is corrosion monitoring. This is all the techniques that we use to monitor. Those are the probes that we would use in the system, and they will tell us what the corrosion rates we are seeing because of H2S or bacterial activity. So that can be electronic probes or in situ corrosion coupons that you normally retrieve. But another thing is something in the digital space that we are working on is to improve these techniques in a way to make sure that we have more digital, remotely operated instruments to calculate corrosion rates. So in terms of bacteria, we also need to monitor them so we can test them. So there's the traditional methods, serial dilutions. So basically you would have the bottles with nutrients that would grow bacteria, and you have sample, you dose into it, and then grow and see how much do you have of those. But there's advanced techniques, quick ones, like ATP techniques. ATP is adenosine triphosphate. Basically, it's an enzyme part of the cell of SRB, of bacteria. So we test for this compound and see how much do we have that in the system. And when it's part of the living organism. So when we kill bacteria, we ideally should see low levels of it. But that's very quick one. It doesn't tell you the amount of species you have across the board. So the next generation is DNA sequencing. So basically that looks into specific species of bacteria. It's a longer term, but it's very detailed, and that way you can determine how much of bad actors do you have in your fluids. And this is how it looks like. So this is different species. By the amount we can see, do we have risk of corrosions, purely H2S, or is it just biofouling? So this is the main thing about the reservoir souring. As I said, this is the area that is emerging during the production cycle, and will have quite a lot of focus in the oil and gas industry, does have and will have, and does require advanced technologies to monitor and control it. So that's mainly it. And I guess we'll take questions after the... Yeah, thank you.